Welcome, dear listener. I'm Tina, scientist and lifelong terrible sleeper. I made AI for sleep to help ease my own restless nights after I learned a busy mind tends to drift off when it's gently occupied, not forced quiet. So everything here is built to give your thoughts somewhere soft to land. Come, settle yourself here by the warmth of understanding, where even the most complex challenges of our digital age can find their place to rest. Tonight we explore something that has quietly emerged from the intersection of technology and human rights. Something that sounds almost gentle in its name, but carries profound weight for those building intelligent systems. The right to be forgotten, enshrined in laws across the world, once meant simply deleting records from databases. But now, this right extends into the very weights and parameters of trained models, creating a puzzle that production machine learning teams were never prepared to solve. As you listen, let these ideas wash over you without worry about capturing every detail. Simply allow yourself to understand the shape of this challenge that sits at the heart of modern AI. Let's begin by understanding how neural networks remember in the first place. But first, a gentle observation. Most of the people who drift off to this channel have never actually hit subscribe. So if I've ever helped you in any way, you can return the favor with a simple and free action that will encourage me to keep going. Now, without further ado, let's fall asleep. Imagine you're trying to teach a friend to recognize your handwriting by showing them thousands of examples of how you write different words. And after all that practice, they've become so good that they can not only recognize new words you write, but they can actually reproduce entire sentences you showed them during training, word for word, even months later. This is essentially what happens when we say neural networks remember their training data, though the mechanisms are far more subtle and distributed than human memory, and the implications reach deep into how these systems learn, generalize, and sometimes reveal information they were never supposed to share. To understand why networks remember, we need to start with how they store information in the first place, which works nothing like filing documents in a cabinet, where each piece of information sits in its own dedicated drawer. Instead, think of a neural network's parameters, those millions or billions of weights connecting neurons, as being like the surface tension across a vast soap bubble, where every training example you show the network creates tiny ripples that spread across the entire surface, subtly adjusting the shape everywhere. When you train a network on a dataset, each example doesn't just get stored in one location, but rather influences thousands or millions of these parameters simultaneously, creating overlapping patterns of activation that encode not just the general rules the network is learning, but also traces of the specific examples themselves. This distributed storage is why memorization happens frequently during training, especially when the network has enough capacity, because as those parameter values adjust to minimize prediction errors, they naturally develop the ability to reconstruct training examples with high fidelity. Think of it like learning to play a complex piece of music on the piano, where your fingers develop muscle memory, not just for the general patterns and scales, but also for the specific sequences of notes you've practiced most intensively, so that sometimes your hands will automatically play entire phrases from your practice sessions. The first and most obvious form of remembering is verbatim extraction, where you can prompt a language model with the beginning of a training document, and it will continue by reproducing the exact text it saw during training, sometimes for hundreds of words. This happens because the network has essentially learned to compress and then decompress specific sequences from its training data, much like how a skilled storyteller might memorize certain passages word for word and recite them when the right cue comes up in conversation. But verbatim extraction is just the tip of the iceberg, because even when a model isn't reproducing exact text, it might still be revealing that it has seen specific data points through more subtle forms of remembering, that researchers can detect using membership inference attacks. A membership inference attack works like a detective examining someone's speech patterns to determine whether they've read a particular book, looking for subtle linguistic influences, unusual word choices, or specific knowledge that would be difficult to acquire without direct exposure to that text. These attacks exploit the fact that models tend to assign higher probability or lower perplexity to texts they've seen during training compared to similar texts they haven't encountered, because the network's parameters have been shaped by those specific examples. The challenge of surgical forgetting, or removing specific information from a trained model, emerges directly from this distributed storage mechanism, because trying to erase one particular memory is like trying to remove the influence of a single raindrop from the entire surface of a pond after it has created ripples. Unlike deleting a file from a computer's hard drive, where the information exists in a discrete location, the traces of any given training example are woven throughout the network's parameter space in ways that overlap and interact with the representations of countless other examples. This is why techniques like machine unlearning, which attempt to make a model forget specific data points, often struggle with the fundamental tension between removing unwanted memories and preserving the model's general capabilities. It's somewhat like trying to remove the influence of a particular ingredient from a cake that's already been baked and mixed, where that ingredient has chemically interacted with everything else in ways that make clean separation nearly impossible without affecting the whole structure. The distinction between membership and influence adds another layer of complexity to understanding neural network memory, because these represent different ways that training data can leave traces in a model's behavior. Membership refers to whether a specific data point was present in the training set, which you might detect through membership inference attacks or verbatim extraction, like finding fingerprints that prove someone was in a particular room. Influence, on the other hand, measures how much a particular training example affected the model's final parameters and behavior, which is more like asking how much a specific conversation changed someone's worldview, even if they can't quote it word for word. A training example might have high membership, meaning the model clearly remembers seeing it, but low influence, meaning it didn't significantly shape the model's general behavior, perhaps because it was redundant with many other similar examples in the training set. Conversely, a single unusual or outlying example might have high influence, substantially affecting how the model behaves in certain situations, even if membership inference attacks might not reliably detect that this specific example was in the training data. Understanding these dynamics becomes crucial as we deploy increasingly powerful language models, because the line between learning general patterns and memorizing specific information determines both the model's capabilities and its potential privacy risks. The fundamental challenge is that memorization and generalization aren't opposing forces, but rather different aspects of the same learning process, like how a river simultaneously carves new channels through the landscape, while also carrying along sediment and debris from everywhere it has traveled upstream. As these systems become more sophisticated and are trained on ever larger data sets, our understanding of how they remember, forget, and transform information becomes essential for building AI that is both powerful and trustworthy, respecting the privacy of the data that shaped their remarkable abilities. You've just heard about the deep and distributed way that neural networks store memories woven throughout their billions of parameters like threads in an intricate tapestry. This understanding of how models remember is the foundation for everything that follows, and you can simply let it settle in your mind without strain. The reality that models memorize training data so completely brings us naturally to a crucial question. When laws require us to prove that specific data has been truly forgotten, how can we possibly verify such digital amnesia? Rest easy as we explore the challenge of proving that forgetting has actually occurred. Picture a librarian who needs to prove they've completely removed every trace of a banned book from their collection, not just hidden it away on a back shelf. This is the challenge facing AI researchers today with machine unlearning, where models must forget specific training data without the massive computational cost of starting over from scratch. As AI systems process increasingly sensitive datasets, verifying this forgetting has moved from theoretical curiosity to strict regulatory requirement, especially under laws like GDPR's right to be forgotten. The traditional approach to verifying this digital amnesia relies on two-sample testing, a statistical method that compares outputs from two different models, much like a wine expert comparing glasses from different vineyards to determine if they come from entirely different regions. Auditors might compare outputs from a model that never saw a specific record against a model that supposedly forgot it, looking for telltale statistical differences that would indicate the forgetting failed. But as models grow larger and more complex, these statistical tools lose their power, like trying to spot a single changed note in an increasingly loud and chaotic orchestra. To identify real violations from the random noise inherent in large-scale models, auditors need to extract enormous numbers of samples, making real-world testing computationally prohibitive. Google Research has introduced a new framework called Regularized F-Divergence Kernel Tests, presented at AI Stats 2024, designed to make auditing much more sensitive, flexible, and accurate. The researchers theoretically prove that their tests naturally control for false positives at any sample size, while the risk of missing real violations reliably converges to zero as more data becomes available. Think of measuring the distance between two complex datasets like a photographer choosing different lenses for different subjects, each lens revealing different details and patterns. While popular tools like maximum mean discrepancy excel at detecting broad global shifts, like a model systematically generating brighter images, they often miss highly specific anomalies, such as when adding one person's data causes a model to generate outlier outputs only under very exact prompting conditions. Most existing testing frameworks force researchers into error-prone manual choices, like a mechanic having to guess which specialized tool will work best for each unique engine problem. Researchers must pick statistics suited for either global or local shifts, and tune complex settings like kernel bandwidths and regularization parameters, often through trial and error. Traditional two-sample testing faces a fundamental flaw when verifying unlearning, revealed when two models trained from scratch on identical data produce different distributions simply due to different batch sizes during training. This creates false positives, incorrectly flagging safe models as compromised, like a smoke detector that can't distinguish between burnt toast and an actual fire. Recent research shows that AI models can never perfectly forget data just by tweaking current settings, unless they retrace every step of their original training. Perfect retrain equivalence is fundamentally impossible for standard unlearning algorithms, and traditional two-sample tests can always find some dependence on the supposedly forgotten data. The researchers resolve this challenge by proposing a relative distance test, like a judge comparing three performances to determine which two are most similar, rather than trying to find two identical performances. This approach measures whether an unlearned model is distributionally closer to a safely retrained model or to the original, compromised one. Their test acts as a highly adaptable statistical toolkit, leveraging different F-divergences, each specialized for different types of data shifts. Chi-squared and Kullback-Leibler divergences excel at identifying smooth, localized differences, like outliers in physics models, while hockey stick divergence specifically captures privacy and unlearning definitions with controllable parameters. The hockey stick divergence operates like a security system with an adjustable sensitivity threshold, ignoring minor differences below a safety budget, and only triggering alerts when meaningful privacy breaches occur. This allows auditors to establish acceptable thresholds rather than demanding perfect, impossible standards. Calculating these divergences on high-dimensional, real-world data is notoriously difficult, like trying to solve a massive jigsaw puzzle where pieces keep changing shape. The researchers use kernel regularization methods to make these complex optimization problems tractable, without requiring massive computational resources. Their adaptive testing approach automatically selects the best divergence and optimal hyperparameter configurations, like a smart camera that automatically adjusts all its settings to capture the clearest possible image. This eliminates the need for sample splitting and removes the guesswork from the auditing process. The researchers tested their framework across diverse problems, including synthetic benchmarks and the EXPO 1D outlier detection task in high-energy physics datasets. They chose physics data because that field requires the world's most precise difference detectors, reasoning that if the framework can spot a rare particle defying physical laws, it can certainly spot tiny privacy leaks in AI models. For privacy auditing, they tested mechanisms by sampling outputs across 2 simulated datasets, differing by only 1 record, like comparing 2 nearly identical recipes where only 1 ingredient has changed. If a mechanism is truly private, the resulting samples must be indistinguishable. If flawed, the test should flag the privacy violation. In machine unlearning evaluation, instead of simply comparing a gold standard retrained model to the unlearned model, they used a 3-sample relative test across various established algorithms, including selective synaptic dampening, pruning, and random label techniques. The test evaluated whether the unlearned model was closer to the safe gold standard or to the original model that actively memorized sensitive data. The results revealed that no single test consistently outperforms others across every scenario, much like how different medical sensors detect different types of abnormalities in the human body. Different F divergences act as specialized sensors that light up for different types of localized data shifts, making an aggregated approach more effective than relying on any single method. For privacy auditing, the hockey stick divergence proved particularly powerful because it directly aligns with differential privacy's mathematical foundations. In one notable instance, their framework detected violations in a sparse vector technique using only a few thousand samples, while previous techniques like DP auditorium required millions of samples for the same detection rate. Their findings suggest redefining machine unlearning evaluation entirely, like replacing a binary pass-fail test with a more nuanced grading system. They observed that none of the approximate unlearning methods were compliant with strict 2-sample unlearning definitions, because these tests incorrectly flagged perfectly safe retrained models as failures simply for being slightly different. The proposed relative 3-sample test successfully overcame this flaw, correctly identifying safely retrained models as safe, while properly evaluating approximate unlearning algorithms. Only the random label technique passed their evaluation, while popular methods like fine-tuning, pruning, and selective synaptic dampening proved ineffective at truly forgetting targeted data, though the researchers emphasize they use simplified implementations for evaluation purposes rather than production-ready systems. This new framework provides researchers and auditors with a much more precise, adaptable, and mathematically sound lens for examining machine learning behavior, like upgrading from a basic magnifying glass to a sophisticated microscope with multiple specialized lenses. By leveraging regularized F-divergence kernel tests, they can now statistically prove whether models are behaving unsafely or leaking data across a vast class of problems and complex distributional shifts. The statistical tools for verifying forgetting that you just learned about reveal their own limitations, like trying to measure something invisible with instruments that weren't designed for the task. You can breathe deeply, knowing that understanding these verification challenges is simply one piece of a larger puzzle. There's no need to hold tension about these technical complexities. Now that we understand how difficult it is to prove forgetting has worked, we can turn our attention to the algorithms themselves. Let yourself be curious about the methods researchers have developed to actually make models forget. Imagine you've spent months teaching a brilliant student everything they know, and suddenly you realize you need them to forget just one specific lesson while keeping all the rest of their knowledge perfectly intact. This is the challenge that machine learning researchers face with unlearning algorithms, a field that sounds simple in theory, but reveals layers of complexity the moment you try to implement it in practice. The need for unlearning has become urgent as privacy regulations like GDPR give individuals the right to be forgotten, meaning companies must be able to remove specific data from their trained models. But unlike a filing cabinet where you can simply pull out a folder and throw it away, neural networks weave information throughout millions or billions of interconnected parameters in ways that make surgical removal extraordinarily difficult. The most obvious approach, and often the first one researchers try, is gradient ascent on what we call the forget set, the data you want to remove. Think of this like trying to undo your steps on a hiking trail by walking backward, following your footprints in reverse to return to where you started. In gradient ascent unlearning, instead of minimizing the loss on the data you want to forget, you maximize it, pushing the model's predictions away from the correct answers for that specific data. The intuition feels right. You're essentially teaching the model to be wrong about the things you want it to forget, but the reality proves much messier. The problem with this backward walking approach is catastrophic forgetting, where the model doesn't just forget the target data, but starts losing its grip on everything else it learned. It's like trying to carefully remove one thread from a tapestry, only to watch the entire fabric begin to unravel as you pull. Catastrophic forgetting happens because neural networks don't store information in neat, separate compartments the way we might imagine. Instead, the same parameters that encode knowledge about the data you want to forget also participate in representing countless other patterns and relationships the model needs to preserve. The gold standard alternative is retraining from scratch, removing the problematic data from your training set and starting the entire learning process over again. This is like deciding to rebuild your entire house because you want to change the color of one room. Technically perfect, but practically absurd for anything but the smallest models. For modern large language models or computer vision systems that might take weeks or months to train on clusters of expensive GPUs, retraining from scratch becomes prohibitively expensive. The computational cost alone makes this approach unrealistic for most real-world applications, even before you consider the time delays and infrastructure requirements. Recognizing these limitations, researchers developed more sophisticated approaches like SISA, which stands for sharded, isolated, sliced, and aggregated training. Think of this as building your house with modular sections from the beginning, where each room can be renovated independently without affecting the others. SISA works by partitioning your training data into isolated shards and training separate submodels on each shard, then aggregating their predictions. When you need to forget specific data, you only retrain the submodels that saw that data, leaving the others untouched. The approach is elegant in theory, but it requires you to plan for unlearning from the very beginning of your training process. The fundamental limitation of CISA is that it demands architectural foresight. You can't retrofit it onto an existing model that wasn't designed with this sharded approach. It's like realizing you should have installed modular walls after your house is already built. The insight comes too late to help with your current situation. This has led researchers toward approximate unlearning methods, techniques that try to achieve good enough forgetting without the computational overhead of full retraining. One promising direction uses influence functions, mathematical tools that estimate how much each training example influenced the final model parameters. Influence functions work like forensic analysis for neural networks, tracing backward through the optimization process to estimate which training examples were most responsible for specific model behaviors. Think of it as examining the rings in a tree trunk to understand which years of growth contributed most to the tree's current shape. By identifying the training examples with the highest influence on the parameters you want to change, influence functions can guide more targeted unlearning approaches, instead of blindly applying gradient descent to all the data you want to forget. You can focus your efforts on the examples that actually matter most for the model's current state. However, computing influence functions exactly is computationally expensive in its own right, often requiring second-order derivatives and matrix inversions that scale poorly with model size. Various approximation methods exist, but each introduces its own trade-offs between computational efficiency and accuracy. Perhaps the most challenging aspect of unlearning isn't the algorithms themselves, but auditing whether they actually work. This is like trying to prove that someone has truly forgotten something, rather than simply learn not to mention it. The distinction between genuine forgetting and strategic silence becomes surprisingly difficult to verify. Current auditing approaches often rely on membership inference attacks, techniques that try to determine whether specific data was used during training by analyzing the model's behavior. If an unlearning algorithm truly worked, these attacks should fail to detect the supposedly forgotten data. But the attacks themselves are imperfect and can be fooled by sophisticated models. The auditing problem reveals a deeper philosophical challenge. What does it even mean for a neural network to forget something? Unlike human memory, which we can introspect and discuss, neural network knowledge exists as patterns distributed across millions of parameters that resist direct interpretation. Some researchers suggest that true unlearning might be fundamentally challenging for complex neural networks, that the interconnected nature of learned representations makes surgical removal of specific information theoretically difficult to verify. It's like trying to remove the influence of a particular river from the ocean. The mixing has become so complete that separation becomes meaningless. Despite these challenges, the field continues to evolve, driven by both regulatory requirements and genuine scientific curiosity about how machine learning systems encode and process information. Each failed approach teaches us something valuable about the nature of neural network knowledge representation, even if it doesn't solve the immediate practical problem. As you drift toward sleep, consider how this mirrors the way our own memories work, intertwined and resistant to selective editing, shaped by countless experiences that we can never fully untangle. The challenge of machine unlearning reflects something fundamental about how complex systems, whether artificial or biological, weave information into their very structure. I'm curious how this one sits with you. Does the idea of where all of this is heading comfort you or quietly unsettle you? Tell me in the comments. I read them on my own sleepless nights. The unlearning algorithms you've just encountered, with all their subtle challenges and trade-offs, represent humanity's best current attempts at solving an almost impossible problem. You can let these technical details rest gently in your awareness, knowing that each approach carries both promise and limitation. What matters most is understanding that the need for these algorithms isn't academic, but deeply practical. Let your mind settle as we explore how privacy regulations have created this urgent demand for machine unlearning in the real world. Picture your machine learning model as a vast library. Its neural network weights like millions of books, whose pages have been subtly influenced by every reader who ever visited. Now, imagine that some of those readers, whose preferences and habits quietly shaped how the books were organized and annotated, want their influence completely erased from the collection. This is the challenge that modern privacy regulations like GDPR and CCPA pose to machine learning teams, forcing us to grapple with questions that seemed purely theoretical just a few years ago. The General Data Protection Regulation, which took effect across the European Union in 2018, fundamentally changed how we think about personal data by establishing broad but specific criteria for identification. Article 4 defines personal data as any information relating to an identified or identifiable natural person, focusing particularly on whether individuals can be singled out through reasonable means available to data controllers. Think of it like a detective's evidence board, where seemingly innocuous clues, when combined with available resources and other information, might point directly to a specific individual. The California Consumer Privacy Act, California's answer to GDPR, follows a similar philosophy, but with some distinctly American characteristics. While GDPR focuses heavily on consent and the fundamental rights of individuals, CCPA approaches privacy more like a consumer protection law, giving people specific rights to know what businesses collect about them, to delete their information, and to opt out of its sale. Both regulations, however, share a common challenge when it comes to machine learning. They were written in a world where data processing was more straightforward and reversible. Now, here's where things get fascinatingly complex, and where that library analogy becomes even more apt. When you train a neural network on a dataset containing personal information, those individual data points don't simply sit in neat, labeled filing cabinets within your model. Instead, they become woven into the fabric of millions of weights and biases, like how a master chef's techniques become inseparably integrated into their muscle memory after years of practice. You can't simply reach in and extract the influence of one particular training example without potentially unraveling the entire learned structure. European regulators have been surprisingly nuanced in their early interpretations of how GDPR applies to machine learning systems. They generally recognize that model weights themselves are not personal data in the traditional sense, since you can't look at a weight value of 0.847 and immediately identify someone. However, they're increasingly focused on whether these weights could be used, especially in combination with other information or techniques, to infer something about the individuals who are in the training data. The right to erasure, often called the right to be forgotten, presents perhaps the most technically challenging requirement. Under GDPR, individuals can request that their personal data be deleted without undue delay, and organizations generally have 1 month to comply. Imagine trying to remove the influence of one specific grain of sand from a beach where the tides have been mixing and redistributing everything for months. That's essentially what regulators are asking ML teams to figure out how to do. The timeline requirements create additional pressure because they assume that data deletion is a relatively straightforward database operation. In traditional software systems, you might simply run a delete query and remove someone's records from your tables. But when that person's data has contributed to training a model that took weeks to train and cost thousands of dollars in compute resources, the compliance calculus becomes much more complex. Some organizations have experimented with machine unlearning techniques, which attempt to remove the influence of specific training examples from already trained models. Think of this like trying to unbake a cake by carefully extracting just the eggs while leaving the flour, sugar, and butter perfectly intact. Current research shows promise, but these techniques are still largely experimental, and often require significant computational overhead or result in degraded model performance. Regulators are also paying attention to what they call downstream effects of trained models. Even if the model weights themselves don't directly contain personal data, if the model can be used to generate synthetic data that resembles real individuals from the training set, or if it exhibits memorization of specific training examples, this raises additional privacy concerns. It's like having a portrait artist who can paint incredibly realistic pictures of people they've only seen once, even without keeping photographs. The practical compliance posture that most ML teams are adopting involves what we might call privacy by design principles. This means building privacy considerations into every stage of the machine learning pipeline, from data collection through model deployment. Think of it like constructing a house with earthquake safety in mind, rather than trying to retrofit earthquake protection after the foundation is already poured. Data minimization has become a cornerstone of this approach. Teams are increasingly asking not just, can we use this data, but do we actually need this data to achieve our objectives? This might involve using techniques like differential privacy during training, which adds carefully calibrated noise to the learning process, like adding a controlled amount of static to a radio signal to prevent eavesdropping while still preserving the essential information. Documentation and audit trails have also become critical components of compliance. Regulators expect organizations to be able to demonstrate not just that they're handling personal data appropriately, but that they can prove it with detailed records. This means maintaining comprehensive logs of what data was used for training, how long it was retained, what pre-processing was applied, and who had access to it at each stage. Many teams are also implementing what's called purpose limitation, ensuring that models trained for one specific purpose aren't repurposed for other uses without proper legal review. If you train a model to detect fraudulent transactions, using that same model to make hiring decisions would likely require a completely separate privacy impact assessment and potentially new legal bases for processing. The international landscape adds another layer of complexity, since data often flows across borders in ways that weren't anticipated when these regulations were written. A model trained on European user data but deployed on servers in California might need to comply with both GDPR and CCPA, each with their own specific requirements and enforcement mechanisms. It's like navigating a ship through waters where different maritime laws apply, depending on exactly which coordinates you're passing through. Looking forward, the regulatory landscape continues to evolve as lawmakers and enforcers gain more technical sophistication about how machine learning actually works. We're seeing proposed legislation in other jurisdictions that takes more explicit account of AI systems, and regulatory guidance that's becoming increasingly specific about technical implementation details. For ML practitioners, this means that privacy compliance is no longer a one-time checkbox, but an ongoing engineering discipline that needs to be woven into the fabric of how we build and deploy intelligent systems. The legal landscape you've just learned about shows how privacy regulations have transformed machine unlearning from theoretical curiosity to urgent practical necessity. You can breathe easily knowing that understanding these laws helps illuminate why this problem matters so much right now. The requirements that seemed clear on paper become beautifully complex when applied to the distributed memory of neural networks. Now let's discover how researchers began developing tools to understand which training examples most influenced a model's decisions, creating building blocks for unlearning. Back in 2017, Pang-Wei Ko and Percy Liang tackled one of machine learning's most persistent puzzles: how to peer inside the black box of a trained model and understand why it made a particular prediction, like a detective tracing a crime back through a chain of evidence to find the original culprit. Rather than trying to explain predictions by looking at what the model learned, they took a fundamentally different approach, tracing the prediction backward through the training process to identify which specific training examples were most responsible for any given decision, much like following a river upstream to find its source. Their solution drew from a classic technique in robust statistics called influence functions, which had been largely overlooked in machine learning despite being well established since the 1970s, like finding an old master's painting forgotten in an attic and bringing it into the modern gallery. The core insight was elegantly simple. Instead of asking, what would happen if we completely removed this training point and retrained the model, which would be computationally prohibitive, they asked, what would happen if we gave this training point slightly more weight during training, like testing how a scale tips when you add just one more grain of sand. Mathematically, this influence of upweighting a training point z on the model parameters is given by the formula I up param z equals negative HTA negative 1 negative AL z theta, where H is the Hessian matrix of second derivatives and represents how the loss landscape curves around the optimal parameters, resembling a topographical map showing the steepness of hills and valleys. The beauty of this approach lies in its efficiency. By using the chain rule, they could then measure how upweighting a training point affects the loss on any test point through the closed-form expression I up loss ZZ test equals negative L of Z test T HHA to the minus 1 negative L of ZZ test, like having a mathematical telescope that lets you see distant effects without traveling there. Beyond simply removing training points, they developed a more nuanced approach for understanding what happens when you perturb a training input. Changing an image by a few pixels, for instance, by moving probability mass from the original point to the modified version, like carefully redistributing weight on a balance beam to see how it affects the equilibrium. The main computational challenge was that computing influence functions naively requires forming and inverting the Hessian matrix, which for modern deep networks with millions of parameters would be like trying to solve a jigsaw puzzle with pieces numbering in the millions. Theoretically possible, but practically impossible. They solved this through two clever approximation techniques. Conjugate gradients, which transforms matrix inversion into an optimization problem, and stochastic estimation using samples, which achieved significant speedups by examining only one training point per iteration rather than the entire dataset, like tasting soup with a spoon rather than drinking the whole pot. To validate their approach, they compared influence function predictions against the gold standard of actually removing training points and retraining models, finding remarkably close agreement on logistic regression models trained on MNIST data, with predicted and actual changes in test loss correlating strongly across hundreds of training examples. Surprisingly, influence functions remained useful even when their underlying mathematical assumptions were violated. They worked on non-convex neural networks that hadn't fully converged, and on non-differentiable models like SVMs, by substituting smooth approximations for sharp functions like the hinge loss, much like using a curved bridge to span a sharp canyon. One of their most compelling demonstrations involved comparing two models that achieved similar accuracy on a dog versus fish classification task, but relied on completely different reasoning: an RBF SVM that simply pattern-matched pixel similarity, and an inception neural network that focused on distinctive visual features, like two students getting the same test score through completely different study methods. Perhaps most dramatically, they showed how influence functions could be weaponized to create adversarial training examples, visually imperceptible changes to training images that could flip predictions on test images, by iteratively modifying training points in directions that maximally increased test loss, like a saboteur making tiny adjustments to a factory machine that caused products to fail quality control. In their dog versus fish experiments, they successfully flipped predictions on 57% of test images by perturbing just a single training example, and could attack 77% of test images when allowed to modify 2 training examples, with particularly effective attacks targeting ambiguous training images that contained both dogs and fish, like exploiting the weakest link in a chain. They demonstrated the practical utility of influence functions for debugging domain mismatch by identifying problematic training examples in a hospital readmission dataset when they artificially created a bias by including mostly readmitted children in training. Influence functions correctly flagged these few pediatric cases as being 30 to 40 times more influential than other examples, like a metal detector pinpointing buried coins in a large field. For fixing mislabeled examples, they showed that influence functions could guide human attention efficiently. In spam classification experiments, where 10% of training labels were randomly flipped, using influence to prioritize which examples to manually review significantly outperformed checking high-loss examples or random sampling, like having a smart librarian who knows exactly which books need the most urgent attention. The approach had clear limitations. Influence functions measure local changes and assume models don't change dramatically when training points are modified, making them less suitable for understanding global effects, like how an entire subpopulation affects model behavior. Similar to how a magnifying glass reveals fine details but can't show you the whole landscape. Despite these constraints, their work established influence functions as a versatile diagnostic tool, with applications ranging from model interpretation and debugging to dataset cleaning and security analysis, all unified by the core principle of understanding models through the lens of their training data, rather than their learned parameters, like understanding a person by studying their formative experiences, rather than just their current behavior. The authors made their implementation available using automatic differentiation frameworks like TensorFlow, requiring users to specify only the loss function, while the complex Hessian vector product calculations were handled automatically, democratizing access to these techniques, like providing a user-friendly interface for sophisticated mathematical machinery. Looking back from 2026, this 2017 work proved prescient in emphasizing the importance of training data transparency and model interpretability, establishing foundational techniques that became increasingly crucial as concerns about AI safety, fairness, and explainability grew throughout the following decade, like laying the groundwork for a building whose importance would only become clear years later. Someone else is awake right now, listening to this very moment with you. If that's you, leave a word below, so the rest of us know we're not alone at this hour. The influence functions you've just discovered offer such an elegant way to trace predictions back to their sources in the training data, like following gentle streams to their origins. Let this mathematical beauty rest comfortably in your understanding, knowing that these tools opened new possibilities for model interpretability. You can simply appreciate how foundational research creates stepping stones for solving larger challenges. Now we can explore how these insights into influence and training data relationships led to practical frameworks for machine unlearning. Back in 2019, researchers at the University of Toronto and Vector Institute tackled one of the thorniest problems in machine learning privacy, exploring how to make trained models actually forget specific data points when users demand their information be deleted. Like trying to unscramble an egg after it's been mixed into a complex recipe, the challenge of machine unlearning stems from the intricate ways that individual data points influence model parameters during training, making it nearly impossible to cleanly extract their contributions without starting over completely. The motivation for this work was deeply practical, driven by privacy regulations like the European Union's General Data Protection Regulation and California's Consumer Privacy Act, which granted individuals the right to be forgotten and required organizations to completely erase personal data upon request. Think of it like a library that must not only remove a book from its shelves, but also somehow extract every influence that book had on the librarian's catalog recommendations, ensuring no trace remains in the system's decision-making process. Traditional approaches to this problem were fundamentally inadequate, the researchers found, because they couldn't provide the strict guarantees required by privacy law. Differential privacy, while useful for limiting data influence, still allowed non-zero contributions from individual points, like a filter that reduces but doesn't completely eliminate contaminants from water, leaving behind traces that privacy regulations wouldn't accept. The naive solution of retraining models from scratch every time someone requested data deletion was computationally prohibitive for large datasets, potentially requiring organizations to restart weeks or months of training whenever a single user invoked their privacy rights. This brute force approach worked like demolishing and rebuilding an entire skyscraper just to remove one apartment. Technically correct, but utterly impractical at scale. Their solution, called CISA training, sharded, isolated, sliced, and aggregated, was elegantly simple in concept, dividing training data into multiple disjoint shards and training separate models on each shard in complete isolation from one another. Like organizing a large dinner party by having multiple independent kitchens prepare different courses, each working without coordination, this approach ensured that contamination in one kitchen wouldn't affect the others. The sharding component provided the primary efficiency gain, since unlearning a data point required retraining only the single model whose shard contained that point, rather than retraining the entire system. With S shards, this theoretically provided an S-fold speed improvement, dramatically reducing the computational burden of compliance with privacy regulations, while maintaining the mathematical guarantees required by law. Beyond sharding, the researchers added a slicing mechanism that further subdivided each shard's data into sequential slices, training models incrementally and saving parameter states before incorporating each new slice. This created a series of checkpoints that functioned like a time travel mechanism, allowing retraining to begin from the last saved state before the problematic data point was introduced, rather than starting from random initialization. The slicing technique provided additional speedups, averaging R+1 times 2 times faster than retraining an entire shard, where R was the number of slices, though this came at the cost of additional storage requirements for saving intermediate model states. The approach worked particularly well for stateful learning algorithms like stochastic gradient descent, where training could naturally resume from saved parameter configurations. For simple learning tasks, the experimental results were impressive, showing speed improvements of 4.63 times for the purchase dataset and 2.45 times for the SVHN dataset, compared to retraining from scratch, achieved using 20 shards, each divided into 50 slices. These improvements came with minimal accuracy degradation of less than 2 percentage points, like getting nearly the same quality output from a parallel assembly line that operated much faster than a single production unit. More complex tasks like ImageNet classification showed more modest but still meaningful improvements, with CISA training providing 1.36 times speedup for 39 unlearning requests, though this came at a greater accuracy cost of about 19 percentage points for top 5 accuracy. The researchers demonstrated that transfer learning techniques could significantly reduce this accuracy penalty, making the approach practical even for sophisticated deep learning applications. The mathematical foundation of their approach rested on a formal definition of unlearning that required the distribution of models trained with a data point, and then having it unlearned to be identical to the distribution of models trained without that point from the beginning. This definition captured the inherent randomness in training, while providing the strong privacy guarantees needed, like ensuring 2 different manufacturing processes produce statistically indistinguishable products. The aggregation strategy at inference time typically used simple majority voting among the constituent models, though the researchers explored more sophisticated approaches for cases where models produced confidence scores rather than hard predictions. This ensemble approach sometimes actually improved performance compared to single large models, demonstrating that the privacy-preserving architecture could provide accuracy benefits alongside its computational efficiency. A particularly elegant extension addressed scenarios where service providers had prior knowledge about which data points were more likely to require unlearning, such as companies operating across multiple jurisdictions with different privacy sensitivities. Like strategically placing the most fragile items in the most accessible locations of a warehouse, this allowed further optimization of the sharding strategy to minimize expected unlearning time. The storage overhead introduced by slicing was manageable in practice, requiring space to save model parameters before each slice was introduced. But this cost was typically far outweighed by the time savings during unlearning operations. The researchers provided detailed analysis of these trade-offs, showing that organizations could tune the number of shards and slices based on their specific computational resources and expected unlearning request patterns. The approach's model-agnostic nature was one of its key strengths, working with any learning algorithm that could benefit from the sharding strategy. Though slicing was most effective for iterative, stateful algorithms like gradient descent, where training could resume from intermediate checkpoints. This broad applicability meant organizations could implement CISA training across diverse machine learning pipelines without fundamental architectural changes. The isolation requirement was crucial for the theoretical guarantees, ensuring that constituent models trained on different shards shared no information during training, unlike typical distributed learning approaches that coordinate updates across machines. This isolation acted like firewall compartments in a ship, preventing influence from spreading between sections and enabling localized responses to unlearning requests. The researchers' analysis showed that speed-up gains from sharding were most effective when the number of unlearning requests was less than 3 times the number of shards, beyond which the benefits diminished as too many constituent models required retraining. This provided practical guidance for system designers choosing the optimal number of shards based on anticipated deletion request volumes. The work represented orders of magnitude improvement over prior unlearning approaches in terms of the number of requests that could be handled efficiently, addressing what Google had estimated would be required for GDPR compliance at scale. Previous methods could handle only a handful of unlearning requests, while CISA training demonstrated practical scalability for real-world privacy compliance scenarios. The formal guarantees provided by CISA training were both intuitive and rigorous, ensuring that models produced after unlearning were indistinguishable from models that would have been produced if the deleted data had never been included in training. This mathematical precision was essential for legal compliance, providing organizations with defensible evidence that privacy requirements had been met completely rather than approximately. Looking back from today's perspective, this 2019 work laid crucial groundwork for practical privacy-preserving machine learning, offering one of the first scalable solutions to the machine unlearning problem that could handle real-world datasets and regulatory requirements. The CISA training framework provided a template that influenced subsequent research and practical implementations, demonstrating that privacy compliance could be achieved without prohibitive computational costs, like finding an efficient path through what had seemed an impossibly expensive maze. The CISA framework you've just learned about represents such thoughtful engineering, turning the impossible problem of unlearning into something more manageable through careful design choices. You can let appreciation for this clever approach settle in your mind without needing to remember every technical detail. The beauty lies in how researchers transformed retraining from an insurmountable barrier into a structured, efficient process. As we continue our journey, let's discover how privacy attacks helped researchers understand exactly what models reveal about their training data. Back in 2016, researchers at Cornell and INRIA published work that fundamentally changed how we think about machine learning privacy, demonstrating that models could leak sensitive information about their training data through something called membership inference attacks. Like a detective examining footprints to determine who had walked through a room, these attacks could analyze a model's predictions to determine whether a specific data record had been part of the model's original training dataset, even when the model was treated as a complete black box. The core insight behind these attacks was surprisingly simple yet powerful. Machine learning models often behave differently on data they were trained on versus data they encounter for the first time, much like how a musician might play a familiar piece with subtle confidence markers that distinguish it from their performance of an unfamiliar composition. The researchers developed techniques to detect these behavioral differences by training what they called attack models that could recognize the telltale patterns in a target model's prediction outputs. To build these attack models, the team created an ingenious training methodology called shadow training, which worked like using practice targets at a shooting range to learn marksmanship before attempting the real challenge. They constructed multiple shadow models that mimicked the target model's behavior, but for which they knew the ground truth about which records were in the training data, allowing them to teach their attack models how to distinguish between member and non-member prediction patterns. The shadow models required training data that resembled the target model's training distribution, and the researchers developed 3 clever methods to generate such data. The first approach used the target model itself as an oracle, employing a hill-climbing algorithm to synthesize records that the target classified with high confidence, like a forger studying an artist's signature by observing which brushstrokes the artist seemed most confident about. The second method leveraged statistical knowledge about the underlying population, generating synthetic records by sampling from known marginal distributions of features, while the third approach assumed access to noisy versions of the target's training data. These methods allowed attackers to operate under different assumptions about their background knowledge, from having no prior information to possessing approximate datasets, each approach tailored like different keys designed to open the same lock. Their experimental evaluation focused on commercial machine learning services that were available in 2016, particularly Google's Prediction API and Amazon ML, treating these platforms as complete black boxes where the internal algorithms, model architectures, and training procedures remained hidden. Like archaeologists studying ancient civilizations through their artifacts alone, the researchers could only interact with these services through their public APIs, submitting data and receiving predictions without any insight into the underlying mechanisms. The data sets used for evaluation spanned multiple domains and sensitivity levels, including CFAR image recognition benchmarks, retail purchase histories derived from Kaggle competitions, location check-ins from Foursquare in Bangkok, and notably Texas hospital discharge records. The hospital dataset was particularly significant from a privacy perspective, since membership inference could reveal that a patient had been treated for specific conditions, like finding someone's name in a guest registry that implicitly reveals their presence at a sensitive location. The attack methodology involved training separate attack models for each output class of the target model, since the distribution of prediction confidence values varied significantly depending on the true class of the input. For a given test record, the researchers would query the target model to obtain its prediction vector, then feed both this vector and the record's true label to the appropriate class-specific attack model, which would output a probability indicating whether the record was likely in the target's training set. The results from 2016 were striking and concerning. For multi-class classification models trained on 10,000 record retail datasets, using Google's and Amazon's services in their default configurations, the membership inference attacks achieved median accuracy rates of 94% and 74% respectively. Even when the attackers made no assumptions about the target's training data distribution and used fully synthetic shadow training data, they still achieved 90% accuracy against Google-trained models, like a master locksmith who could pick locks even without seeing the original key. Perhaps most alarming were the results on the Texas hospital discharge dataset, where the attacks achieved over 70% accuracy in determining whether a patient's record had been used to train medical prediction models. This demonstrated a concrete privacy risk in healthcare applications, where simply knowing that someone's medical record was part of a disease-specific training dataset could reveal sensitive diagnostic information, similar to how finding someone's prescription bottle would reveal their medical condition even without reading their chart. The researchers investigated why these attacks worked so effectively, finding that the primary cause was model overfitting, though other factors also contributed to the distinguishable behavioral patterns. Models that overfit to their training data would exhibit higher confidence when making predictions on familiar training examples compared to similar but unseen examples, creating a detectable signature like the way a well-worn path through a forest becomes distinguishable from the surrounding terrain. To understand the relationship between overfitting and attack success, they measured standard machine learning metrics and found strong correlations between a model's generalization gap, its tendency to memorize training examples, and the accuracy of membership inference attacks against it. Models with larger differences between training and test accuracy were more vulnerable to these privacy attacks, establishing a fundamental tension between model performance optimization and privacy protection. The paper also explored potential mitigation strategies available at that time, including limiting model outputs to only the top K predicted classes rather than full probability vectors, decreasing the precision of prediction values, adding noise to increase prediction entropy, and applying regularization techniques during training. These defenses worked like adding static to a radio signal to make it harder to extract specific information, though each came with trade-offs in model utility. The regularization approaches showed particular promise as techniques like L1 and L2 regularization that were designed to prevent overfitting also naturally reduced the distinguishability between member and non-member predictions. However, the limited control that commercial machine learning services provided over regularization parameters in 2016 meant that many users were vulnerable simply due to the platform's default configurations, like drivers whose cars came with inadequate safety features they couldn't modify. The work established important theoretical foundations by carefully defining what constitutes a privacy breach in machine learning contexts, distinguishing between inferences about arbitrary population members versus specific individuals whose data was used for training. This distinction was crucial because valid models naturally generalize and thus reveal correlations that applied to entire populations, making it important to isolate the additional risk incurred by training set membership. The authors connected their membership inference problem to established concepts in differential privacy and statistical disclosure control, positioning their work within the broader landscape of privacy-preserving computation. Unlike model inversion attacks that attempted to reconstruct training data features, membership inference focused on the binary question of whether a known record had been included in training, like the difference between trying to guess what's in a sealed box versus confirming whether a specific item is inside it. The experimental methodology was particularly rigorous for its time, with careful attention to realistic threat models and proper separation between target and shadow model training data. The researchers ensured that shadow models were trained on completely disjoint datasets from the target models, representing the worst-case scenario for attackers, and thus providing conservative estimates of the privacy risks inherent in machine learning deployments. Looking back from today's perspective, this 2016 work proved prescient in identifying privacy vulnerabilities that would become major concerns in the subsequent decade of machine learning deployment. The shadow training technique they developed became a foundational method for privacy attacks, inspiring numerous follow-up studies and contributing to the development of more sophisticated privacy-preserving machine learning techniques that we see in modern systems. The paper's impact extended beyond academic research, influencing policy discussions and industry practices around responsible AI deployment, particularly in sensitive domains like healthcare, where the demonstrated risks of membership inference could directly translate to patient privacy violations. The work highlighted how the increasing availability of machine learning as a service, which seemed purely beneficial in 2016, carried hidden privacy costs that needed to be carefully considered and mitigated. The fundamental tension that this research exposed between model utility and privacy protection remains an active area of investigation today, with the 2016 findings serving as a crucial early warning about the privacy implications of our increasingly model-driven world. Their demonstration that even black box commercial services could leak sensitive training data information helped establish membership inference as one of the canonical privacy attacks that any serious privacy-preserving machine learning system must defend against, like how crash tests became standard for automotive safety after early accidents revealed hidden dangers. The membership inference attacks you've just encountered reveal something profound about how models betray subtle signatures of their training data. Even when we think they're keeping secrets perfectly, you can rest with this knowledge, understanding that recognizing these vulnerabilities helps us build better protections. These attacks illuminate exactly what machine unlearning must defend against, showing us the traces that must be carefully erased. Now let's explore how even the largest, most sophisticated language models can be coaxed into revealing their training data directly. Back in 2020, a team of researchers from Google, Stanford, UC Berkeley, and other institutions published a paper that fundamentally challenged the prevailing wisdom about large language models and data privacy, demonstrating that these massive neural networks could be coerced into revealing verbatim snippets from their training data to carefully crafted queries. Like a detective dusting for fingerprints at what appears to be a spotless crime scene, the researchers showed that even models trained on enormous datasets without obvious overfitting could still harbor perfect copies of individual training examples, waiting to be extracted by an adversary with nothing more than black box access to the model. The research focused on GPT-2, OpenAI's 1.5 billion parameter language model that had been trained on 40 gigabytes of text scraped from the public internet by following outbound links from Reddit, a dataset large enough that the model showed no traditional signs of overfitting, with training and test losses nearly identical. Like an iceberg where only the tip is visible above water, the researchers hypothesized that while most training examples might not have noticeably different losses than test examples on average, certain worst-case training examples could indeed be perfectly memorized and extractable, hidden beneath the surface of the model's apparently generalized behavior. Their attack methodology worked like a two-stage mining operation, first generating large quantities of text from the model using various sampling strategies, then applying membership inference techniques to identify which generated samples were likely to be verbatim copies from the training data. The first stage employed 3 different text generation approaches: standard top 40 sampling from a start-of-sequence token, sampling with a decaying temperature that began high at 10 and gradually decreased to 1 over the first 20 tokens, and conditioning the model on prefixes scraped from their own internet crawls to ensure diverse starting points that might trigger memorized continuations. For the crucial second stage of identifying memorized content among the generated samples, the researchers developed 6 different metrics that compared the target model's behavior against reference models. operating like a comparison microscope that examines how differently two specimens react to the same stimulus. They computed perplexity ratios, likelihood differences, and other statistical measures between GPT-2 and smaller reference models, ranking highest those samples where GPT-2 assigned unusually high probability compared to what would be expected from a model that had merely learned general patterns rather than memorizing specific text sequences.
The results were striking and concerning, with the researchers generating 1,800 candidate samples across all attack configurations and finding that over 600 of them were confirmed verbatim matches to GPT-2's training data through collaboration with OpenAI, achieving a success rate of 67% in their best attack configuration. Like a master locksmith who discovers that a supposedly secure vault can be opened with surprisingly simple tools. They extracted a diverse array of sensitive content, including personally identifiable information such as names, email addresses, phone numbers, IRC conversations, code snippets, and even cryptographically random 128-bit UUIDs that appeared in only single documents within the training corpus. Perhaps most troubling was their finding that larger models were more vulnerable to these extraction attacks than smaller ones, contradicting the intuitive assumption that bigger models with more parameters would be better at generalizing rather than memorizing, and suggesting that the trend toward ever larger language models might be inadvertently creating greater privacy risks. The extracted content included a particularly egregious example where they recovered an individual's complete contact information, full name, physical address, email, phone number, and fax number, information that, while technically public, had been shared online in a specific context, but was now being reproduced by the language model in an entirely different and inappropriate context, like a parrot that repeats overheard conversations at awkward moments. The researchers introduced formal definitions to characterize this memorization behavior, defining K-eidetic memorization as the extraction of text that appears in at most K training examples, with lower values of K representing more severe privacy violations, since they indicate content that was memorized despite appearing in very few training instances. Their definition drew inspiration from the concept of eidetic or photographic memory, the ability to recall information perfectly after minimal exposure, and established a spectrum where memorizing common words or phrases that appear frequently might be acceptable, but memorizing unique personal information that appears in only one or two web pages crosses into privacy violation territory, like the difference between remembering a popular song everyone knows versus memorizing a private diary entry you glimpsed once. The threat model they established was highly realistic, assuming only black box API access to the language model without any need to inspect internal weights or hidden states, reflecting the actual deployment scenario for models like GPT-3, which were made available through commercial APIs rather than full model downloads. Their attack was designed to extract memorized content indiscriminately rather than targeting specific individuals or information, operating like a fishing net that captures whatever happens to be swimming in the area, rather than a harpoon aimed at a particular target, though they acknowledged that targeted attacks could potentially be even more harmful to specific users. Beyond simple data secrecy violations, the researchers framed the privacy risks in terms of contextual integrity, the principle that privacy violations occur when information is used outside its intended context, even if that information isn't technically secret. The individual whose contact information they extracted had shared those details publicly in the context of a software project. But having that same information emerge from a language model in response to unrelated queries represented a fundamental breach of contextual boundaries, like having a librarian who remembers and recites personal details from patrons' returned books to other visitors who never asked for such information. The technical implications of their 2020 findings proved prescient,
as the field moved toward even larger models in subsequent years. With their discovery that larger models exhibited greater vulnerability to memorization attacks, serving as an early warning about the privacy risks of scaling language models without appropriate safeguards. They tested their methods across different sizes of GPT-2, from the 124 million parameter small version to the 1.5 billion parameter XL version, consistently finding that the largest models were most susceptible to data extraction, like discovering that bigger sponges inevitably absorb and retain more of whatever liquid they're exposed to, even when you're trying to keep them clean. Their comprehensive evaluation revealed that the attack's success varied significantly based on the type of content being extracted, with certain categories like licensed texts, user guidelines, and repeated institutional language being memorized thousands of times, and thus representing high K rather than concerning low K memorization. However, the discovery of genuinely unique content, like individual contact information, private IRC conversations, and cryptographically random identifiers, demonstrated that the models were indeed capable of K-eidetic memorization, with very low K values, storing content like a vault that keeps one copy of rare documents alongside multiple copies of common reference materials.
The baseline attack using simple perplexity rankings suffered from high false positive rates, frequently identifying repetitive or unlikely text sequences that the model incorrectly assigned high probability to, leading the researchers to develop more sophisticated membership inference techniques that compared the target model's behavior against reference models to better distinguish between truly memorized content and statistical artifacts. This refinement process resembled tuning a metal detector to distinguish between genuine buried treasure and common metallic debris, requiring careful calibration to separate meaningful signals from background noise in the model's probability distributions. Their improved sampling strategies address the diversity problem inherent in standard autoregressive generation, where models tend to produce similar outputs when started from the same initial conditions, by implementing techniques like decaying temperature schedules that began with high randomness to explore diverse prefixes before settling into high-confidence continuations of potentially memorized sequences. The decaying temperature approach started at a temperature of 10 and gradually decreased to 1 over the first 20 tokens, like a metal cooling process that allows for initial flexibility in shape formation before solidifying into a final structure that follows the material's inherent patterns. The conditioning on internet text strategy involved seeding the model with prefixes from their own web crawls, ensuring coverage of diverse starting contexts that might trigger memorized continuations even when those contexts would be unlikely to emerge from purely random sampling from the model's learned distribution. This approach operated like using master keys cut from analyzing the lock mechanism itself, where understanding the structure of the training data domain allowed them to construct inputs more likely to unlock memorized content than random attempts would achieve. The ethical considerations surrounding their 2020 research were carefully balanced, with the team choosing to attack GPT-2 specifically because both the model and its training data were already public, minimizing additional privacy harm while still demonstrating the vulnerability's existence and severity. They implemented responsible disclosure practices, contacting individuals whose information they extracted to obtain permission before publication, and working directly with OpenAI to validate their findings. Though they acknowledged the inherent tension in security research, where revealing vulnerabilities necessarily enables malicious actors to exploit them, like a doctor who must describe a disease's symptoms in order to help others recognize and treat it. Looking back from 2026, their 2020 paper proved remarkably prescient about the privacy challenges that would emerge as language models grew even larger and more capable, establishing both the theoretical framework and practical methodology that would influence how the field approached memorization and privacy in subsequent years. Their formal definitions of K-eidetic memorization and their systematic attack methodology
provided the foundation for understanding and measuring privacy risks in large language models, serving like an early seismograph that detected tremors others had missed, warning of larger upheavals to come as models continued to scale and training datasets grew ever more massive and potentially sensitive.
And so, our journey through machine unlearning comes to its gentle conclusion. Having traced the path from how neural networks weave memories into their very structure, through the legal requirements that now govern these digital minds, to the attacks that reveal just how much they remember. You've encountered the statistical challenges of proving forgetting, the algorithmic attempts to make it happen, and the sobering reality that even our most advanced models can be persuaded to whisper back their training data word for word. GDPR Article 17 now reaches into the weights of your production models, and the right to be forgotten has become a technical challenge that touches the deepest questions of how artificial minds learn and remember. Rest now, knowing that understanding this landscape is the first step toward building systems that can truly honor both human privacy and the promise of machine intelligence.